Hello and welcome to our presentation in AR-assisted reconfiguration and workspace visualization of malleable robots. In this presentation, I'll begin by introducing you to the research aim, and then I'll summarize the methods from literature in human-robot interaction, what is achievable and what is novel. I'll then introduce you to the system we developed and its key elements. Finally, I'll end by walking you through some of the experiments to demonstrate the capabilities of the system. A classical robotic manipulator is designed with a task in mind and requires 6 DOFs to achieve unconstrained motion in 3D space. But the higher number of DOFs comes with it higher costs and weight. As robotics continues to evolve, researchers are seeking ways to minimize DOFs while making the manipulator suitable for a wide range of tasks. This led to the creation of malleable robots. The main idea behind it is to incorporate the malleable link into the robotic system. This is a link that has variable stiffness that's enabled via layer jamming controlled by pressure. When the link is soft, the user can then change the robot link parameters, the distance and orientation between the revolute joints, thus allowing for different robot configurations to be achieved. The malleable robotic system achieves different workspaces by changing its end effector pose within a maximum reachable space. But there are no easy ways to inform the user of where to position the end effector to achieve a task. This discrepancy creates a new challenge, which is to create a communication, visualization, and interaction system to identify the user's needs, communicate that to the robot, and achieving that through successful human-robotic collaboration. As a result, the purpose of this work is to develop an AR system that enables interactive workspace generation, visualizes the workspace and its outcomes, is revolutionary in terms of its workflow, and provides all of that within an ergonomic package. The roots of human-robot interaction stems from human-to-human interaction, such as gaze, speech, posture, and gesture techniques. On the other hand, robot visualizes its trajectory in the form of its start and end positions. And for its extent of motion, the system may display its workspaces in a 2D slice and overlay it on top of the camera footage. However, it is very difficult for the user to interpret the spatial features. To solve this issue, we can then use AR. Existing literature has utilized AR to achieve trajectory and forward kinematics visualization, while also taking the user into account by asking them to rate the quality of a solution. However, when it comes to malleable robots, there are no existing solutions. Therefore, we're proposing our own. To begin by developing the system, it is critical for us to understand what is achievable by the malleable robot in terms of its topology and its workspace. When the robot's not fixed in space, the user is free to position the end effector as long as it lies within the reconfiguration space, defined as the volume at which all points in the space are theoretically reachable with a malleable link topology. And this is limited by the minimum and maximum curvature of the robotic arm. This is generated via cycloid and involute curves, which traces out this volume. On the other hand, we have the reconfigured workspace, which is the more traditional definition of a robotic workspace. This represents all the points that's reachable by the robot once the malleable link is rigid. These workspaces look similar to standard robotic configurations such as SCARA, spherical, general articulated, and planar. The workspaces are generated via distance geometry and triangulation. The topology of the malleable link is defined via 4 distances, D13, 14, 24, and 23, which are the 4 straight distances between the points 1, 3, 1, 4, and such. They fix the relative position of the end effector with respect to the base joint. Using an algorithm that's developed in the REDS lab, these 4 distances were computed and can be used to place the end effector at a unique location. These distances are then presented to the user in the form of a distal link placed in the user's view. Here's the AR interface. When the user first opens up the app, they can see the lectern and the robot base. The user interacts with the lectern, which then has an instruction panel. The robotic base is then, which is a holographic object, can then be overlaid on top of the actual robotic base. As it is being placed, it becomes the world anchor, and this is where all of the other holograms are defined with respect to. Finally, the distal link, which the user places down in the reconfiguration space as they desire, which is used later for reconfiguration. The detailed AR reconfiguration workflow is presented on the diagram on the right. We begin with the user manually align the hologram to the robot base, followed by the configuration definition, which is done using the holographic distal link, both of which are done manually. The scene is then saved and the distal link positions are extracted for computation. These points positions are then passed to the workbench, which computes the desired malleable robot topology, workspace, and end effector locations, then are reloaded into the scene and paired with animation to guide the user for reconfiguration. Now we will analyze the system performance. First, as the system that relies on manual alignment, we would like to assess the user's initial alignment errors when positioning the robot base. We measure the error between the HoloLens's end effector points P3 and P5 and their real counterparts. We took 5 samples of 3 points, and we took an average across them and arrived at a mean value of 10.54 plus or minus 4.32. From literature, this alignment error can be as high as 16, and it can be as low as 1 to 2 in surgical AR systems. Secondly, we assess the overall task performance of the system when it comes to reconfiguration accuracy. What contributes to this error is the alignment error from the user, but also from the physical flex of the robot itself. Here we assess how closely the user can align the real end effector to a target end effector position. In this experiment, we asked 5 participants to run the app and measure the actual end effector distances at distance lengths. On average, the absolute mean reconfiguration error is 9.64 plus or minus 2.06, and on relative terms, 3.54% plus or minus 2.57%. These results actually outperform some other HMD systems found in teleoperation. Finally, we conducted a NASA TLX study, which is a subjective workload test on the user. In this questionnaire, there are 6 unique components: mental workload, physical workload, temporal workload, performance, effort, and frustration. Then using these components, we generated a composite score of the entire system. It is desirable for the system to score as low as possible except for performance, and the score we obtained was 42.83, while in literature, the number can range between 35 and 60. In this work, we illustrated the development of an HRI system for assisting user reconfiguration of valuable robots. We offer an AR pipeline for reconfiguration, but also a new perspective on 3D motion planning. Through testing, we then evaluated the system's accuracy in tasks by looking at the error on alignment and reconfiguration. Finally, we proposed to upgrade the system by improving the AR headset to reduce holographic drift, and then incorporating automatic registration techniques to further enhance system performance. Thank you.